All right, we're looking at section 9.1, sum and difference identities. Now, if you're not in the Belhaven trig class for some reason and you're watching this, we're using the OpenStax textbook, Algebra and Trigonometry. So this chapter is all about identities, and we've looked at a lot of them. We looked at Pythagorean and quotient, and what else did we do? The reciprocal identities, and we had a few others, but those were the main ones that we needed. So now we're trying to address this question. If I had something like this, sine of angle A plus B, the temptation is to always write this as sine A plus sine B. There's a temptation to do that, and that is very, very much false. You cannot do that, all right? So as an example where you could see that this doesn't make any sense, if I had sine of pi over 2, and I recognize that as sine of pi over 4 plus sine of pi over 4, or in other words, I'm recognizing that pi over 2 is pi over 4 plus pi over 4, then you'll notice here that's not going to work because sine of 1/2 we know is 1, and sine of pi over 4 is root 2 over 2, and root 2 over 2 plus root 2 over 2 just gives me square root of 2, not 1. Okay, so see, we made an error here. So what we need is some identities. Oh, that is actually equal. We need some identities to help address how we deal with this. Okay, so I'm not going to, well, let's just list them out. Okay, so we'll start off sum and difference identities. I'll just give you the sine and cosine versions of these. And then we'll do a tangent one, and I'll show you where the tangent one comes from. I'm not going to really show you where the sine and cosine ones come from. They come from using the distance formula and some other identities, and just for our time, I don't feel like that's something we need to go over. But if you do have a question on that, I can go over it with you sometime. All right, so the first one we're going to have is if I have sine A plus B. So the first two we'll do are sine. Okay, they look like this. You say sine A, sine B, so that's multiplication, minus sine B, oops, sorry, cosine A, cosine B. That's sine of A plus B. No, it's not. That's incorrect. Sorry, my coffee hasn't kicked in. Sine of A plus B is sine A cosine B plus sine B cosine A. Sorry, the symmetry there is that for the sines, well, I'll show you, but for the sines, it's sine then cosine, but then you keep the same sign. Yeah, for the subtraction then, by that same pattern, we say, what's going on? There you go. Sorry, my screen froze for a second. Sine A cosine B minus sine B cosine A. All right, so it's, again, you're keeping, you're changing your trig functions, sine A cosine B, and then you're keeping the sign, the plus or minus. Now, the reason I say that is because for cosine, it's what I wrote originally. First you say, for cosine, you say cosine A, cosine B, minus sine A, sine B. And for subtraction, you have cosine A, cosine B, plus sine A, sine B. All right, so notice the symmetries again. for the sines, you have different trig functions, but you keep the same sign, right? The trig functions differ, keep the same sign. For the cosines, you keep the same trig function, but the signs differ. Keep the same trig function, but the signs differ. And that's the pattern. And that's kind of the way you have to memorize it. All right, now I'm going to go over some examples to show how we can apply these things. It is very useful, believe it or not. So I'll give you an example of why. All right, so I'll follow along with the text examples. Example 1 from the book. We want to find, we want to find cosine of 5 pi over 4 minus pi over 6. Okay, so we know how to evaluate these individually. I know how to find cosine of 5 pi over 4 because I have a reference angle of pi over 4. I know how to find cosine of pi over 6, but do I know how to find them when they're subtracted? Well, I'm going to use my identity here. Which one should we use? It's a subtraction with cosine, so I'm using what I listed as number 4 for my list here. Okay, so I'm going to have cosine of 5 pi over 4 minus pi over 6 is, according to my identity here, cosine of 5 pi over 4, cosine of pi over 6, right? That's cosine A, cosine B, plus sine A, so that's sine 5 pi over 4, sine B, sine of pi over 6. Okay. Now, I know it's been a while since we've thought about these things, but we have to remember now how to evaluate each one of these. So, first of all, for the 5 pi over 4s, remember you have a reference angle of pi over 4. Sine and cosine of pi over 4 is root 2 over 2. And we just have to worry about plus or minus. So I think 5 pi over 4, well, 1 pi is 4 pi over 4. So 5 pi over 4 is down here somewhere in the third quadrant, which tells me that these are both going to be negative root 2 over 2. Right, they're both negative root 2 over 2. And we remember that because sine and cosine of pi over 4 are both square root of 2 over 2. Now, for pi over 6, we have to say, let's see, cosine of pi over 6, this is just memory work, is square root of 3 over 2. And sine of pi over 6, if you remember, is 1/2. So for that reason, I can now multiply all these together. And let's see, we get negative root 2 over 2 times root 3 over 2 should give me the square root of 6 over 4 plus negative root 2 over 2 times 1/2 gives me negative root 2 over 4. And since I have a common denominator, thankfully, I can write this as one expression. This is negative root 6 minus root 2 over 4, and that is my solution. Okay, that is the value of cosine 5 pi over 4 minus pi over 6. And I hope this makes sense. And again, if you have a question, make sure to leave it in the comment section, and I will try to address it for you. Okay, now you may have never thought about 5 pi over 4 minus pi over 6, but you may have thought about this angle. So let me write this one down for you. Example 2, let's find cosine of 75 degrees. I want to know cosine of 75. .75 is not one of my common reference angles, so I don't know this one off the top of my head. But what I do know, or what I can think about, is 75 is the sum of two of my common angles. Right? Couldn't I say 75 is the same as 45 plus 30? That should give me 75. So I can use that and my identities here to figure out what cosine of 75 degrees is. All right, so like this. I know then that cosine of 75, which is the same thing as cosine of 45 plus 30. All right, so if you want to, you can say that this is angle A and that's angle B. Will then have to be, let's see, what's the cosine of A plus B identity? Remember, for cosine, it's going to be, you keep the same trig function, so it's going to be cosine A, cosine B, flip the sign, minus sine A, sine B. So it's going to be cosine A here is 45 degrees, cosine 30 degrees, minus sine 45 degrees, sine 30 degrees. Right. And again, you just have to remember it. And I'm trying to go over the symmetry to help remember it, but at the end of the day, you just have to remember these. Okay, now from there we know all these values. I know that cosine of 45 degrees is square root of 2 over 2. I know that cosine of 30 degrees is root 3 over 2, right? Sine of 45 is root 2 over 2, and sine of 30 is 1/2. And notice that those are actually the same numbers we dealt with last time. So I know when I multiply these out, I'm going to get root 6 minus square root of 2 all over 4. And there is my solution. There it is. I hope these make sense. All right, now let's try another one. I'm trying to think. We haven't done a sine one. All right, so let's do one with sine. And I'm changing mine from the books a little bit. Why don't we do sine of 15 degrees? Sine of 15 degrees. Okay, which we recognize as sine of, well, what's my common angles and give me 15 degrees? How about 45 minus 30? Does that work? I could have also done 60 minus 45, right? But we'll just go with this one. All right, so I'm doing a sine subtraction. Let's go back and look what our identity was for that. Sine A minus B, you change your trig value. So you have sine A, cosine B, but you keep the sign, what I mean, the plus or minus. So it's going to be sine A, cosine B, minus sine B, cosine A. Okay? So let's see if we can remember that. So we have sine A, cosine B, right? You change your trig values, but we keep the plus or minus. So that's going to be minus sine B, cosine A. So I have sine 45, cosine 30, minus sine 30, cosine 45. And we know all these values, right? And it's going to actually be very similar to what we just did, I think. Let's see. Cosine of 45 is root 2 over 2. Yeah, this looks very familiar to me now. Cosine of 30 is root 3 over 2. Minus sine of 30 is 1/2. Cosine of 45 is root 2 over 2. And I get the square root of 6 minus root 2 all over 4. I get the same thing I had in the previous example, right? They're exact same. So let's pause for a moment, okay, because this is a concept not directly related to what we're talking about, but it is one we need to keep in mind. It's one we've discussed already. We just said that sine of 15 degrees is the same thing as cosine of 75 degrees. And if we had thought about it, we would have known that before we went through all this. How do I know? Because remember, the cofunction identity, we said that sine theta is the same thing as cosine of 90 degrees minus theta. or you can flip that around if you want. Cosine theta is the same as sine of 90 degrees minus theta. Alright, so the reason that helps here is because this is the same thing as cosine of 90 degrees minus 15. And notice that 90 minus 15 is 75. So it completely makes sense that sine of 15 degrees and cosine of 75 degrees are actually the same thing. Okay, now let's look at an example that deals with some inverse trig functions that we have dealt with before, but are easy to forget about. But if you do have them, you can do something like this. So this is example 4. I want to find the exact value. So when we say exact value, we mean you can't use a calculator, right? The decimal value is not exact. Here's what we want. We want to know the sine of cosine inverse of 1/2 plus sine inverse of 3/5. I want to know exactly what that is. Okay, now, at first you're thinking, wait a minute, sine of what? So we have an addition statement in here, and we have these inverse trig functions, but you have to plug in an angle into a trig value. But remember, the inverse trig functions are angles, right? What comes out of them is the angle. So this is angle A, and that is angle B. And what we'll want to do, so let's rewrite this first of all as sine A plus B. Okay, so using my trig value, my trig identity, let's at first expand this out to see what that would look like. Okay, so we're doing sine. So remember, I changed my trig values. My trig functions. I have sine A, cosine B, but I keep the same sign. So that's sine B plus sine B, cosine A, like that. All right, so now from there, I just need to figure out what I need to know. What I need to know: sine A, cosine B, sine B, cosine A. And can I do that from the inverse trig functions? Yes, I can. All right, so we're gonna have to do a little bit of scratch work. Here, cosine inverse of 1/2 equals A is another way of saying cosine A equals 1/2. And here we need to mention, if you remember, that only works if A is in the first two quadrants for cosine inverse. That's how that works. Okay, so we know that A is in the first two quadrants. But if I have that, then I can figure out what, let's see, I know then what this is, right? I know cosine A. Can I figure out sine A? Well, yeah, and you could do that either from identities or a triangle. I'll do one of each. For the first one, let's do a triangle here. All right, so I have a right triangle. Cosine is adjacent over hypotenuse. So that means I have one side, the adjacent side, here's A, by the way. The adjacent side is 1, the hypotenuse is 2. So from Pythagorean theorem, we'll call this opposite side y. I know that 1 squared plus y squared equals 2 squared, which is 4. So y is going to equal the square root of 4 minus 1, which is the square root of 3. And it will be positive because my cosine value is positive, and so I know I'm in the first quadrant. Okay, so that tells me then I know now I can figure out sine A, right? Because sine A, if you remember, is y over r, or in other words, root 3 over 2. So there's that one. We got our sine A and cosine A. If you want, we can go ahead and write that out. Sine A is root 3 over 2. We don't know cosine B. We don't know sine B, but we do know cosine A was 1/2. Okay, so I know those parts. Now I just need to do the same thing with angle B. Okay, now for angle B, I could use a triangle again, but remember I said you could use a triangle or identities. I'm going to use the identities here because I just want you to see it. All right, so for, let's see, I'm trying to pick a color that kind of distinguishes it. All right, so looking at sine, I know that sine inverse of 3/5 equals b, which is another way of saying that sine of b equals 3/5. Okay, so from that, can I figure out what cosine b is? Yes, because remember, sine squared b plus cosine squared b equals, and I can hear you shouting through the TV screen or the computer monitor that that's going to be 1. All right, so here algebraically, then I can say that's 3/5 squared plus cosine squared b equals 1, or cosine squared b equals 1 minus, let's see, 3/5 squared is going to be 9 over 25. So 25 over 25 minus 9 over 25 gives me 16 over 25. And so cosine b could be plus or minus, but here it's going to be plus 4/5. How did I know it's plus? Because my inverse sign was positive. That means I'm in the first quadrant. And for the first quadrant, cosine is positive as well. All right, so that tells me then I can come back and plug in the missing numbers from earlier. Sine b was 3/5. Let me try that again. And cosine b was 4/5. And so there I have all my missing pieces. Okay, is this making sense? I hope so. All right, so all this here was kind of my scratch work. And it's not exactly scratch. It's what I had to do to figure out my missing pieces here. All right, my sine A, cosine B, sine B, cosine A. And so now, to finish this question up, we just need to multiply that out. So I'll try to bring it all the way down here. And so finally, I get, let's see, what was our original expression? I'll write it again. Sine of cosine inverse 1/2 plus sine inverse of 3/5. And we just said that that's going to be root 3/2 times 4/5 plus 1/2 times 3/5. And so notice you get 4 square root of 3 plus 3 all over 10. And there's my solution. There's my angle. And that is not a number you would have guessed, right? It may not even be a number you recognize, but it is an exact number, okay? It's the exact value of this expression here. So the sine A plus B is allowing us to figure out things that we couldn't do earlier, like sine of 75 degrees and other addition statements. All right, now you also may want to know about tangent. Okay, so I'll show you how that works as well. So, and I'll actually show you how to get the tangent identities. Okay, so if you had tangent A plus B, what I know from the quotient identities is that that is sine over cosine. All right, so we just applied the quotient identity. And then I can expand those each out using the identities that we've learned today. Sine of A plus B, right, for sine, remember, you flip your cosine, your trig statement, your trig function, you keep the same sign. So that's sine A cosine B times sine B cosine A over the cosines you keep the same and you flip the sign in the middle. All right, now This looks like it's getting very, very complicated. It's actually going to reduce kind of nicely for us. What I'm going to do is I'm going to multiply in a 1 over cosine A, cosine B to both the numerator and the denominator. That sounds really weird, but watch what happens when you do that. So I get all this sine A, cosine B, plus all that, all over cosine A, cosine B, divided by all this other stuff over cosine A, cosine B. Still looks very confusing. Okay, but when I split this up like this, so look, since this numerator here has a common denominator, I can break it up as two different fractions, like this, sine A, cosine B, over cosine A, cosine B. So there's my first expression, plus sine B, cosine A, over cosine A, cosine B. Okay, and notice when I do that, some stuff starts happening. Cosine B cancels out. I'm left with sine A over cosine A. The cosine A's cancel out. I'm left with sine B, cosine B. Okay, now in the denominator, what happens? In the denominator, doing the same idea, cosine A, cosine B over that thing, minus sine A, sine B over that denominator again. Notice this first expression all reduces down to 1. Okay, now, so applying, and notice in the second expression, let's see if I can highlight what's going on here. Sine A over cosine A times sine B over cosine B. Alright, so now applying the quotient identities, I kind of like this yellow. Let's go with this yellow. That means I have finally tangent A plus tangent B, right? Because sine over cosine is tangent, over 1 minus tangent A times tangent B. And that is the tangent A plus B identity. So let's call that number 5 in this game that we have, right? So tangent A plus B is tangent A plus tangent B all over 1 minus tangent A times tangent B. For subtraction, you do the same thing. We're not going to go through all of it. It's the same identity we just had. You just trade your signs. The plus becomes a minus in the numerator, and the minus becomes a plus in the denominator. And there's number 6. Okay, it's pretty cool. Alright, so what this will allow me to do now is just go through examples like we just did, now with tangent. Alright, so let me do one. So this is example 5 in the textbook. I want to find tangent of pi over 6 plus pi over 4. Okay, now this is a tangent A plus B situation. So that means I'm going to have to just apply that identity, and we do have to remember them. And just for the sake of our discussion here, pi over 6 is A, pi over 4 is B. So that, what did we say that was? Let me look at it again. Tangent A plus B is tangent A plus tangent B over 1 minus tangent A times tangent B. So that's going to be tan pi over 6 plus tangent pi over 4 all over 1 minus tangent pi over 6 times tangent pi over 4, like that. Okay, now we remember what those values are, right? Let's see. Tangent of pi over 6, and if you have to remember, you can think, well, that's sine over cosine. Sine of pi over 6 is 1/2. Cosine of pi over 6 is root 3 over 2. So when you combine those, you get 1 over root 3. Tangent of pi over 4 is 1. And then in the denominator, we just use those same things, 1 over root 3 times 1. Okay, now another way of doing this, well, let's see, what do we get? Another way of thinking about tangent of pi over 6, some textbooks use this value, root 3 over 3, which is the same thing as 1 over square root of 3, right? If you rationalize it, you get root 3 over 3. I think here, though, it doesn't really matter either way. I don't think it'll help us either way. What I'm going to do is in my numerator, I'm going to get a common denominator, right? So instead of writing 1, I'm writing square root of 3 over square root of 3. And you know what? I'll do that in my denominator as well. And so now when I add, I get 1 plus square root of 3 over root 3 over root 3 minus 1 over root 3. And from there, remember that dividing by a fraction is the same as multiplying by a reciprocal. So that's going to be times square root of 3 over root 3 minus 1. I can see that the square root of 3's will cancel out. And I'm left with 1 plus square root of 3 over the square root of 3 minus 1. And there is my value. There it is. And I hope this makes sense. If I'm going through this too quickly, I apologize. Leave me questions if you have them. Also, I will have this document, so you can kind of see here my notes. I'm going to have these notes posted in a PDF on Canvas, and I'll have it as a link in the description of this video as well. Okay. So what I would like to do from here, let's see. Let me look at another example. I got 2 more examples I want to cover. The first one is I want to verify. So we're doing a verifying identity. If you remember how we did that, I'm going to verify sine a plus b plus sine of a minus b equals 2 sine a cosine b. So if I add sine a plus b and say sine a minus b, that's actually the same thing as 2 sine a cosine b. Now, if you remember, verifying identities, what we mean is you're basically doing a proof statement, right? You're going to start with one side of the equation, the more complicated side of the equation, and hopefully deduce the other side of the equation. Okay, so what we're going to do here, which side's more complicated do you think? Definitely the left side. All right, so we're going to use the left side and try to reduce it. Okay, so from the left side, I know sine a plus b. Let's see, how do we do this? Remember, you change the trig value, but you keep the sign. So there is sine a plus b. Sine a minus b is the same deal, right? You trade the trig function, but you flip the sign. All right. So if I'm adding these together, I end up with sine a cosine b plus cosine a sine b, that's the first one, plus sine a cosine b minus sine b cosine a. All right, all of that is supposed to equal 2 sine a cosine b. We'll see if it does. But notice when I'm subtracting, cosine a sine b and sine b cosine a are the same thing. They subtract out. and I'm adding the same term here together. So I end up with 2 times sine A cosine B equals 2 sine A cosine B. And I believe that's a true statement. So there it is. We've identified it. Now, verifying identities with sum and difference identities can be complicated. We won't do a lot of them, but I did want you to see one. I want you to see how it goes. Okay, now the last thing we're going to do is I want to show you an applied problem, because this stuff does show up in the real world, right? By the way, that was example 8 from the textbook. Okay, so let's look at example 11. And here's the situation. Okay, so we have a climbing wall. I'm going to try to draw a picture here. We have a climbing wall, something kind of like this. All right, and you have to have some sort of guy wire. So you have one attached up here at the top, and you have another one attached somewhere here. All right, and if you come out 50 feet, that's where they are fixed. So that's a 50 feet span, and you have one wire coming like this, and you have the other one coming out like this. Okay, now what I know is that the first one is at the top of this wall, which is 47 feet. And then the second one is attached at 40 feet high, like that. All right, so we say for a climbing wall, a guy wire is attached 47 feet, and they call this one R. On a vertical pole, added support is provided by another guy wire S, which is 40 feet above the ground on the same pole. If the wires are attached to the ground 50 feet from the pole, find the angle alpha between the two wires. Okay, so what we want to find is this little angle here that we're calling alpha. All right, now what we're going to need to do that is actually have this angle as well, which we call beta. Okay, so we're going to need to figure these out. Now, where do we go from here? Okay, so what do I know? I know the opposite and the adjacent side of these two triangles. The triangle involving S and then the triangle involving R. Opposite and adjacent would be which trig value? Or trig function? That would be tangent, right? So here I know tangent. I know, let's see, I do know tangent beta is going to be opposite over adjacent. So that's 47 over 50. There's tangent of beta. Now I also know tangent involving this angle, but how do I express that angle? Well, that angle, isn't that the big angle beta minus angle we're looking for alpha? So actually I know tangent of beta minus alpha, and tangent of beta minus alpha is 40 over 50, which will reduce down to 4/5. Okay, so I know those, and I'm trying to find tangent alpha. Can I do it? Well, yeah, because we know another way of expressing tangent of beta minus alpha in terms of tangent beta and tangent alpha, which is what we needed. Okay, so let's go ahead and do that. Let's apply our identity. Tangent of beta minus alpha, we know. What's the trig function? The trig identity. You want to see it again? Come up here. There it is. This is the one we're using. Tangent alpha minus beta, or A minus B here, is tangent A minus tangent B over 1 plus tan A times tan B. Alright, so we're going to try that. That's tangent beta minus alpha is going to be tan beta minus tan alpha over 1 plus tan beta tan alpha. Okay, and we know some of this stuff. Let's see. I know tangent beta. So I have 47 over 50 minus tan alpha. Actually, let me come down and write it below because we know something on the left side of this equation as well, right? I know that tangent beta minus alpha is 4/5, and I know that tangent beta is 47 over 50. We don't know tangent alpha, so we're trying to figure out 1 plus 47/50 tangent alpha. And I can use algebra to figure out and solve for tan alpha, which is what we're going to do. Okay, so I multiply both sides by this denominator. Sorry, where'd it go? I'm going to multiply both sides of this equation by my denominator and end up with 1 plus 47/50 tan alpha times 4/5 equals 47/50 minus tan alpha. All right, and from there, let's see, what would I do? How about I multiply both sides of my equation also by 5? And the reason I like to do that is because now I have 4 times 47/50 tan alpha equals 5 times 47/50 minus tan alpha. It got rid of the 4/5, and it's going to kind of reduce some of my work for me. So I have 4 times 47/50 tan alpha, distributing the 4 there, and 5 times 50, 5 and the 50 divide, so you get 47 over 10 minus 5 tan alpha, like that. All right, so when I do that, I end up with 4, and let's go and bring in our calculator here. 4 times 47 over 50 is going to be, if you plug it in your calculator, it should be 3.76 tan alpha equals 4.7 minus 5 tan alpha. So now when I add the 5 tan alpha to both sides of my equation, I end up with 8.76 tangent alpha equals, subtracting 4 from both sides, I get 0.7. So tangent alpha is approximately 0.07991. How did I get that? I said 0.7 divided by 8.76. And so then my alpha value, which is what I'm looking for, is going to be approximately tan inverse of that number. And when you take the tan inverse of that, you'll get approximately, let's see, 0.07971. Okay, that is my angle. That's alpha in radians. All right, so going back to the picture, this alpha is that number that we just got, the 0.079741. Now, the thing is, though, since we deal with degrees mostly, we probably want to convert this back to degrees. How do I do that? I'm going to say 0.07971 times, remember going from radians to degrees, you need to multiply by 180 and divide by pi. And so when you do that, you get approximately 4.57 degrees. And there's my degree measure of the angle between the two cables, which may be something that we really need if we're constructing this climbing wall. All right. I hope this makes sense to you guys. The big takeaway is you have to know your sum and difference identities, all 6 of them, the sine, cosine, and tangent. And to know them well, you need to know the other identities as well. So make sure, if you don't, know your Pythagorean identities, your quotient, and your reciprocal identities. Those are all important. Okay, now what I'm going to do from here, again, is I'm going to post this PDF on Canvas, and I'm also going to post a link to this PDF on the description of this video. If you have any questions, let me know. If you don't feel like this is working, we can try something else. And we'll pick up a little bit after 8 o'clock again here on Thursday. If you need to come back and watch this later, you're welcome to. And thanks for watching.